Hi guys, welcome to our ongoing discussion, next chapter of our discussion about ligand binding as this sort of fundamental layer of protein function, right? So last time we ended the lecture considering this idea of thermodynamic linkage and its role in ligand binding, specifically in the incredible physiologic role this plays in oxygen transport, specifically oxygen binding to hemoglobin, right? I pointed out that the problem that we have in terms of oxygen transport by hemoglobin is that we need to load and unload oxygen from hemoglobin across this really quite narrow range of partial pressures of oxygen. Specifically, we need to go from, somewhere around, say, 40%, 30 to 40%, to something like 90% across a partial pressure range of something like about threefold, right? So we need this nonlinear binding behavior. We need to have this molecule that can tell how much oxygen is around and change its overall affinity based upon the number of molecules bound, essentially, or the ambient ligand concentration. All right, so I pointed out that this is this type of curve, of course, is something you've seen before. This is a cooperative curve. This sort of is directly connected to this idea of linkage, right? Thermodynamic linkage. And I pointed out you've seen this before in the context of protein folding and the linkage of all those interactions that hold a well-folded globular protein together. So the question now becomes, how do we describe this in the context of ligand binding, specifically oxygen binding to hemoglobin? All right, well, to begin with, let me just point out something. This is an example of a type of cooperativity that is known as homotypic cooperativity. And it's known as homotypic cooperativity because in this case, all the ligands, this would be, partial pressure of O2, all the ligands involved in this binding interaction are the same. It's the same ligand. So it's thermodynamic linkage all within the same type of ligand. There's also heterotypic linkage, which we'll come to later. But specifically from the point of view of thinking about oxygen binding to hemoglobin and this idea of homotypic cooperativity and oxygen binds to hemoglobin, the question is, how do we explain that, right? Okay. The idea that something was really weird with hemoglobin, that something not like other binding interactions with other simple protein systems had to be the case with hemoglobin was really first recognized some time ago and really sort of taken head on in a quantitative way to begin with in around 1910 by a man named Archibald Hill, right? And Hill, in addition to recognizing that there was something weird about this, he had another problem. He knew, and others had known in the recent past of Hill's work, that hemoglobin had to be binding more than one oxygen molecule per protein molecule. But they had no idea how many binding sites hemoglobin had in the first few years of the 20th century. And so Hill sat down and tried to develop a quantitative approach to predicting that based upon things he could measure, right? And so what Hill said was, well, all right, let's say we got hemoglobin and it can bind some unknown number of oxygen molecules. So we can write that out as hemoglobin bound to O2 in moles of O2. Okay, fine. For our purposes, let's go back to that nomenclature as fewer letters that I like to use. So we'll go P for protein, A for ligand, this time really A, right? And then our complex would be PA sub N. Okay. So we know we can, in principle, we could write down an equilibrium constant associated with that equilibrium. And we'll define it as a dissociation constant. So that would mean K would simply be equal to concentration of P times the concentration of A. But since we've got multiple moles per event, we've got to raise that to an exponent, right? Divided by concentration of PA in that fully liganded complex. Now, note something very important here. This derivation is assuming something, right? This assumes that binding is all or nothing, right? That all those ligands go on sort of in a single event. Okay, that's going to become important later. All right, so now what do we do? Well, we could start off sort of the way we did before and go back to the degree of binding, but it turns out that in these binding events that have higher order or higher molecularity, more things bind, there's another parameter that people often use, and it has some advantages, right? And that's known as the fractional saturation. And it's given the symbol capital Y, right? Okay, and the fractional saturation, rather than number of moles of ligand bound for total protein, is simply the concentration of the fully liganded protein divided by the total protein concentration, right? Therefore, fractional saturation, right? Okay, that's also, if you think about it, that's also equivalent to just taking the degree of binding, which we defined before, and dividing by the number of moles of ligand bound, or the sort of number of binding sites, if you think about it that way, right? Which would be equal to just N times concentration of PA to the N divided by concentration of P plus concentration of PA sub N, right? Because that's our old definition, divided by 1 over N, right? So this first part would be equivalent to the degree of binding divided by N. You essentially get the fractional saturation. Okay, now why do this, right? Well, think about it this way. In the limit, right, here as sort of A goes to infinity, what does the fractional saturation go to? Irregardless of the molecularity, irregardless of the binding stoichiometry. It goes to 1, right? So the fractional saturation is going to vary between 0 and 1. But if you do the same thing for the degree of binding, right, that's going to go to N, which is fine. Sometimes you want to know what that stoichiometry is. But that means the degree of binding, if you think about plotting this stuff out, is going to vary with molecular symmetry, right? The fractional saturation, the advantage of using fractional saturation is that you can always describe it as varying between 0 and 1, the fraction of the protein found. Okay, so let's use that definition, right? And we're going to combine it with this definition for the equilibrium constant here, right? And we do that, what we find, of course, is that we can rearrange the binding constant definition. So let's do that, right? So let's say K. Now we're just going to rearrange this thing like we've done before. Excuse me. So we're going to solve it for that, the concentration of the fully liganded state, right? Because we want to use that to substitute into our degree, our fractional saturation, just like we did before. Same basic procedure for this derivation. So we solve it that way. It means our fully liganded molecule is simply equal to the concentration of P times the concentration of A to the N divided by K. That's cool. So now we can take this, substitute that in here, right? And we do that, and we now end up getting an expression for the degree of binding, fractional saturation. I keep doing that. Fractional saturation that looks like this: P concentration of A to the N divided by K divided by concentration of P. Ah, come on. Concentration of P plus concentration of P, concentration of A to the N divided by K. And now I've done this enough times, you should see where we're headed here. Cancel, 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 multiply through by K. And you do that, your degree of binding now reduces to this. It's simply concentration of A to the N divided by K plus concentration of A to the N. Cool, that's simple, right? That's not too bad, right? But if you look at that for a second, in the context of the way we've been thinking about, in particular, what these constants mean. We think about them as dissociation constants, equilibrium constant, right? And if you look now at this expression here, you see a problem there? You should, if you look at it for a second. For anything, for any derivation in which n is greater than 1, what would the apparent units of K have to be? Again, we're going to do the biochemist thing of thinking about this as a quantity with some units associated with it, the way we would think about KDs. What do the units have to be? They have to be whatever n is, right? So that K has to be, if we think about it again, like a dissociation constant, it's like, micromolar, it has to be micromolar squared or cubed, or for hemoglobin, it have to be to the 4th power. How do you think about that? I mean, it can't be a dissociation constant the way we've been talking about it. We're thinking about it. It can't be like a macromolecular, a macroscopic binding constant. It's certainly not a microscopic binding constant. I mean, 4th power? All right, that's a little weird. Okay, so think about it this way. What's another way that you can define, or you can think about the way we talked about it before? We thought when we talked about the simple single site binding, right? Those hyperbolic binding, degree of binding expressions, right? And you could define this as fractional saturation as well. Remember what happened right there at the half saturation point? The concentration of the ligand, whatever it happened to be, at that point is equal to the dissociation constant, right? You guys remember that, right? Oh, so that's kind of useful, right? Because what that means then is we could think about the half saturation point. So look what happens if we say, well, all right, fine. What happens if I set the fractional saturation? Oh, geez. If I set the fractional saturation as equal to 0.5, right that halfway point. And like, okay, well, that's got to just be equal to concentration of A to the N divided by K plus concentration of A to the N. Huh. What that means, right, is that for that to be true, at the half saturation point, even for this exponentially impacted binding phenomenon, K has to equal the concentration of A to the N, right? At the point of half saturation, right? Which I can write like that, right? In order for that expression, if you substitute that in there, to work out to 0.5. So what that lets us do then is to sort of operationally define a K apparent, in this case, for the purposes of our little derivation here, as equal to the concentration of A at half saturation, which means, right, we can rewrite the degree of binding expression as equal to the fractional saturation equals the concentration of A, our ligand, raised to the N, divided by K apparent raised to the n plus the concentration of A raised to the n. And that's exactly the expression we're looking for. I'm going to change that up just a little bit more by adding an additional notation. It looks like this: A raised to the n sub h divided by K apparent raised to the n sub h plus A raised to the n sub h. That is the so-called Hill equation. Right? Okay. So you think about that K apparent, right? It's not a real dissociation constant, but it's kind of an operational one, right? So the point of half saturation, the amount of ligand you got to put in to get half saturated, gives you kind of an apparent, an average sense of how well the ligand binds. So it's kind of proportional to an average binding affinity for that ligand. Even though it's not a true affinity, it's not a microscopic affinity, it gives you kind of an average sense of the strength of the binding, right? How much ligand you got to get in to get half saturated. The other thing that you should note from this equation is my addition of that little sub h there, right? It's the same exponent, but I put the little h on there. And the reason I did that is because this exponent in this equation gets a special name. It's known as the Hill coefficient. Right? And it's a very important parameter in thinking about molecular allosteric and ligand binding in systems like this, right? So the Hill coefficient tells you some really important stuff about a system like this, right? So one thing, if you just think about that, right? If you think about how the Hill coefficient would vary in an expression like that, right? So if the Hill coefficient is equal to 1, what kind of binding do you have? It just looks like a hyperbola. It looks exactly like a normal single site binding expression, right? Right? In this case, and it could have more than, the molecularity could have more than one binding site, but that Hill coefficient 1 means there's nothing going on. They're all independent. They might as well just be, isolated binding sites. There's no cooperativity at all. And in this case, the expression basically, or the binding behavior reduces to what you've seen before. It's just a completely hyperbolic binding plot. Okay. If the Hill coefficient is between 1 and n, what does that mean? You guys know? It means you have something called positive cooperativity. Right? If the Hill coefficient, and this ascent never really happens, but if the Hill coefficient were to equal 1, so were to equal n, that would be so-called perfect. That would be, it's called perfect or infinite cooperativity. And like I said, that doesn't really ever happen, right? But here's another one. If the Hill coefficient is less than 1, is something known as negative cooperativity. We talked about that a little bit in terms of those characteristically concave up scatter plots, right? Which have gotten people in lots of trouble over the years, right? So positive cooperativity, of course, tells you that the binding of each ligand makes the binding of the next ligand more favorable. Negative cooperativity is the opposite. The binding of each ligand makes the binding of another similar ligand more difficult, right? So the binding, the thermodynamic linkage is opposite, right? Because of positive cooperativity, each ligand is driving an increase in affinity of the next ligand. negative cooperativity, it's going the other way. Each ligand makes binding of the next ligand more difficult. All right. All right, remember though, Hill's goal here, right, was to try and figure out how many binding sites hemoglobin had. That was the whole point, right? That's why he sort of went through this little exercise. And the problem for Hill was that when you do this, you can do it, people have done it a lot over the last century. The Hill coefficient for hemoglobin is around 2.3 to 3.0 for hemoglobin, depending upon the conditions and the solvent solution conditions, right? So operationally, if you think about the goal here, Hill failed, right? This model didn't accurately predict the number of hemoglobin binding sites, right? And Y is absolutely contained in the assumptions of the model here, that the binding model assumed essentially all or nothing binding. Despite that flaw, and despite the fact that it didn't work, this is still an incredibly important equation for you guys to know, an important phenomenon for you guys to know, in particular, the Hill equation, right? And the reason is because the Hill equation and the Hill coefficient are considered to be incredibly important operational parameters for the extent of cooperativity in or how cooperative a cooperative system happens to be. So if you think about that, right, within this range here, right, think about what those plots would look like, right? A non-cooperative system, right, is of course going to have that simple hyperbolic curve, whereas a cooperative system, right, is going to start showing those nonlinearities, right? It's going to start doing stuff like this, right? And the thing is, the more cooperative the system, oops, the steeper that nonlinearity, right? So as the Hill coefficient goes up, those curves become more and more and more nonlinear. They get the sigmoid gets steeper and steeper and steeper as a function of the underlying ligand concentration here, right? So if this was fractional saturation, this was 1, 0, here's our ligand concentration. As the Hill coefficient goes up, it requires a smaller and smaller change of smaller and smaller change of the ligand concentration, right, to get you to saturation, right? Okay. Okay. So even though the Hill coefficient, the Hill equation is considered this, incredibly useful sort of operational tool for assessing the extent of nonlinearity, the extent of cooperativity in a system. As a predictor of hemoglobin's number of binding sites, it failed. Because it assumes this all or nothing binding, right, is the main reason why that failed. And the additional problem here, in addition to giving the wrong number, right, ultimately, people had already proven that model assumes, like I said, that all the binding kind of happens in one go. It sort of predicts, as written down, that there are no partially liganded species. It's 0 or 4. People knew within a few years of Hill trying to do this, that was wrong, that partially liganded species could be observed. So the underlying assumption of this model, to some extent, doesn't work, right? All right. But nonetheless, I keep pointing out that you're going to still see the Hill equation used a lot because its assumption, it sort of sets an upper bound, if you want to think about it. The most cooperative type of system would be one that was infinitely cooperative. And you can operationally compare how nonlinear a given system is. If you're working on a new system, you just want to characterize it with a single parameter, you can characterize that nonlinearity with that Hill coefficient. All right, but it's not a, wasn't a great model for accurately understanding the number of binding sites hemoglobin had. All right, so the question was, what happened then? Well, the next attempt at this was by someone known as Gilbert-Adair around 1925. A man named Gilbert-Adair took another stab at this. And Adair had an advantage that Hill didn't have. He had access to a brand new, super high-tech, cutting-edge technique. You may have heard of it. It's known as electrophoresis. Wow, I mean, it was super high-tech for the day. All right. All kidding aside, this technique allowed Adair to do accurate assessments of the number of subunits, number of binding sites that hemoglobin had. And he was able to establish that hemoglobin had to have 4. So he had an independent measurement of the number of binding sites. And what Adair went on to do was then to say, well, okay, what kind of a model would let me accurately describe, as a function of oxygen binding, the degree of binding, this hemoglobin binding curve? So he's like, okay, all right, well, let's say I've got a hemoglobin, and we're not going to make the same assumption that Hill made. We're going to say, okay, so I've got hemoglobin. I know I got 4, so we're going to bind 1, and then we've got hemoglobin O2, and we're going to have a dissociation constant. So now this is closer to like what we think of as a dissociation constant. Only got 1 ligand. Okay, and then we can say oxygen, another oxygen. And so now we're going to have hemoglobin O2 2, K2. Okay, and then we can do another one, right? Hemoglobin O2 3, and we could do another, and we get K3, right? Okay, well, that's cool. The neat thing, some way you can go through the math, you can derive an expression. In the case of hemoglobin, it'll have 4 constants. These got a name. They were known as the so-called Adair constants. And if you do this, and you take some data and you take the expression that comes out, it will beautifully fit binding of oxygen to hemoglobin. You get a great fit. Really, really good. Here's the problem. What does it mean? If hemoglobin's a symmetric molecule, which if you looked at that structure, at least, you know, in sort of the basic structure of hemoglobin without any oxygen bound, it's basically symmetric, right? There's some differences. There's some small subtle difference, but to a first approximation, it's a symmetric looking molecule. How would a symmetric molecule change its affinity if each of those binding sites is basically the same? And symmetry, you know, there's an important rule in a lot of biology. It's not nearly as strict as people thought it was once upon a time. We'll come back to it when we talk about some other models of cooperativity. If symmetry, nature tends to want to maintain symmetries at a molecular level like this. How would a molecule like that ever change its affinity, right? The point here is that the Adair equation that comes out of this, which I'm not going to write down, right, can beautifully mathematically fit binding of oxygen to hemoglobin, but has absolutely, it's quantitative, right? Works beautifully. It has 0 mechanistic or predictive value because the model itself doesn't explain in any way where these different binding constants come from, how they could be encoded in the structure. It just sort of assumes that that happens, right? And out comes a perfectly good phenomenological model with no predictive mechanistic value. All right. So that's where things sat for about 30 years or so, until two different groups working independently from each other came up with two different models of oxygen binding to hemoglobin that took the first steps towards a mechanistic explanation of how this could happen, right? And we'll take a look at that next time.